All right. In theory, you guys have just completed your first assignment on limits, a brand new concept, something to wrap your minds around that is new. I don't want to call it complex, but it's very different than what you've been asked to consider before. On the worksheet that you downloaded, you should have done the first 20 problems 1 through 20. So let's check those out. I'm not going to really go through the answers so much because the answers are all in the back of your course pack. I want to make sure you guys are aware of that. There's like 30 um, pages of not just really answers, but solutions. I mean, some of them are just answers that don't really explain where they came from, but a lot of the problems are worked out in full. So please be willing to check your work as you go. If you get stuck, don't just stop or don't wait a full day to go on. Go back and look at how the problem was worked out, and it may get you going again. Um, maybe you don't understand why they did something, or maybe you don't understand what step was taken. You don't follow like line 3 to line 4. And those are really good questions to ask me. I can answer those fairly quickly if you come to the tutoring session, or just shoot me a message. But please use that as a resource. I will go through these problems for you though. Quickly, just so you can see how you were doing. Problems 1 through 6, we're giving you some pictures, and then asking you to evaluate the limits. Each one kind of wanted you to do a left limit, left one-sided limit, a right one-sided limit, and then the two-sided limit. The actual limit is what we call the two-sided limit. And then what is the function's value at the point in question, at the x value in question? So here we go. As we approach, what are we approaching? 3. As we approach 3 from the left, right, from the negative side, what height am I at? Well, it looks like I'm at a constant height of 3, and that's why the answer up here is 3. On the other hand, as I approach 3 from the right, so I come in this way, the function actually has a height, constant height, let alone of 2. Heights don't have to be constant, but that's easy, makes it easy to track them. And so that's why the answer up here is I said 2, I meant negative 2. Um, and so here's the thing about part C, and this was a big piece of our lecture yesterday. A limit will only exist. The limit will only exist. It's two-sided limit will only exist if the two um, the two one-sided limits agree, if they're equal to each other, because that means that as we come from the left and the right, um, we're approaching the same height, and that definitely doesn't happen. 3 is not equal to negative 2, and that's why the answer for C is that the limit does not exist. Now, what is f of 3? That's not equal to either one of those. I mean, the way that this function is defined, f of 3 has a height of 1. And now, that doesn't really matter as far as limits are concerned, but we'll find out that does matter as far as something else is concerned. But these two things matter immensely. These have to agree for this to exist. I won't go through the other 5 problems quite as slowly, but just to talk you through kind of a review of what we were discussing yesterday. Okay. Number 2, what's happening as I approach 4 from negative 4 from the left? So here we come into negative 4, and the function is kind of here, and then up toward a height of 1, 2, 3, 4, 5. Okay, so the left limit is 5, um, and now the right limit. Here we come in from the right. We're kind of following this curve down and up. Looks like the height is 2. Okay, well, 5 is not equal to 2. And so that's why for part C, the limit does not exist. D and E. That's really all you need to say. D and E does not exist. What is the function's value at -4? Well, according to this graph, the closed dot is at a height of 2. Okay, so the right limit agrees with the function's value, but because of the jump discontinuity, the limit doesn't exist. Number 3, where are we approaching? We are approaching 0. 0 from the left, 0 from the right. So 0 from the left is coming in here. And it looks like we're approaching a height of -4-ish. Looks like a little less than that actually, but we'll call it -4. On the other side, we're coming in from the right, and our function's approaching a height of, oh, look at that, -4. We're approaching the same height. Okay, that's good. That means that this guy exists and is equal to that limit. So you can see that these have to all be the same if this guy exists. Now what's really nice is that f of 0 is also equal to -4, and that is going to play a major role in a future conversation. It's a concept we talked about back in Unit 1, and I'm not trying to be secretive, but I don't want to ruin the future. Let's see here. This one, a lot of people are going to look at this and freak out right away because they see this big jump discontinuity, and they're going to be like, oh, you can't do this problem. But they're asking about this function at -2 back here. Okay, so there's not a problem. As I come in from the left, I'm approaching a height of 3. As I come in from the right, I'm approaching a height of 3, which means the two-sided limit is 3, right? So the limit as we approach -2 of p of s is 3, and p of -2 itself is equal to that same height of 3. Just a look to the future. This is a really interesting thing right here. It's called a cusp. If you have like an absolute value function that changes direction very abruptly, not nice and smooth like a parabola, but very abruptly, we call that a corner. And it's gonna cause us problems in calculus in certain instances. When you have something that's curving, concave, increasing, and then suddenly goes, the exact opposite, like decreasing very quickly, it creates something even sharper than a corner. We call that a cusp, and it definitely causes problems in calculus. We don't really care as far as limits go, but just thinking of the future there. Number 5, we are approaching 0 with these limits. 0. Well, that's a problem. I see at 0, there's this big old jump discontinuity that's going to cause issues. The left limit is approaching a height of +4. The right limit is approaching a height of -3, which means this guy right here, the two-sided limit, does not exist. It looks like the closed circle up here is at 4. So f of 0 itself is 4. And then finally, number 6, what's happening at 2? What's happening at 2? This is a really interesting problem. We haven't seen one like this yet, so let's make sure we understand this. The height I approach from the left, the height I approach is just 1, okay? The height I approach from the right, well, look at that. It's the same height. I'm approaching a height of 1. So this is 1, and this is 1. And if these two things are equal, then this thing is the same. It's also 1. Now notice that the actual function's defined value at 2, g of 2, is up here at 3. This is 3. Okay? This dude doesn't care what this value is. This dude only cares that these guys are the same. That's where limits are different than algebra, okay? Or at least one of the big areas. Limits only care about what we're approaching, not what's actually there. So I think what we've learned through examples and then some of these homework problems is that at removable discontinuities, limits are still going to exist because we're approaching the same height from both sides. But at jump discontinuities, um, that's not going to hold true. That's why we had problems with problems 1 and 2. Also, on problems like number 6, if we approach the limit from 0, 0 from the left, 0 from the right, we would get infinity because of the vertical asymptote there. That's an infinite discontinuity. Infinity is not a real number, and so the limits would not exist there either. And that is what we're going to be talking about next week, or infinite limits. So big conversation for next week. All right. The next, like, what, 10 problems ask you to find limits through substitution and then support graphically. I'm just going to tell you really quickly how I know that all of these can be found using simple substitution. The first three, this guy, and this guy, they're just polynomials. This guy's a really crazy polynomial with a huge power, but these guys, just second power, actually if you multiply it'll be a third power, this guy's a third degree. These are polynomials. Polynomials are continuous everywhere, and hence you can find their limits anywhere by just substitution. Now, number 10 and number 11 are rational functions, so you have to look out. What causes a 0 in the denominator, right? -2. What causes a 0 in the denominator here? It would be the square root of 3. Actually, also the square root, the negative square root of 3. Um, so we have problems there, but I know that these are going to be, I'm going to be able to use substitution because I'm not taking the limit at -2. I'm taking the limit at +2. 2 plus 2 is 4. That's not a problem. -3 squared is 9. 9 minus 3 is 6. See, I'm not getting zeros in the denominator, which means the rational functions are fine. Remember, the domain of a rational function is everywhere except x values that cause zeros in the denominator. Not an issue. Now this one makes me a little bit concerned because the greatest integer function jumps, right? Every integer there's a jump discontinuity. Oh, but look, I'm not taking the limit at an integer, so that's okay, right? This makes me a little nervous because it's a radical function, but check it out. The root is an odd root. Remember, even roots are limited, but odd roots exist everywhere. So once again, I'm not worried about it. The square root function does make me nervous, but this guy, if I set x plus 3 um, greater or equal to 0, remember that's how we did things back in good old Unit 1. We know that the domain of the square root of x is all non-negative values, right? Non-negative greater or equal to 0. So x's have to be greater or equal to -3. That's why this one's okay. 2 is within the domain. We can just substitute. This one probably scared you a lot because of the e to the x and the cosine of x. Not that you didn't spend an entire semester on cosine of x last semester, right? But they're both continuous all the way. You know, e to the x looked like this. Domain all real numbers. Cosine of x looked, like that's a terrible drawing, but like this, all real numbers. Um, so there aren't going to be any issues there. Sine of x is also continuous. Now the natural log of x isn't defined at 0 or negative numbers, but pi over 2 is a positive number, so you're good to go. So just before we get into breaking these down a little bit, um, I can just glance at these and be like, hey, I can do all of these through substitution because the functions are either safe or the functions are safe at the values that we're defining them at, right? These functions are bad some places, but not at these places. And so that's why we don't worry about it. But let's take a quick glance at them. If I plug a -3/2 into this function, and you'd have to show the algebra, you would want to show 2 times -3/2 is -3, -3 minus 1 is -4, and then multiply that by whatever -3/2 squared times 3 is, and get your value, okay? Not a big deal. Turns out to be, I believe, negative negative 3 halves. Oh, I'm sorry, I was plugging negative 3 halves in. I was supposed to plug negative 1 half in. So that would be negative 1 minus 1 is what? Negative 2. Negative 1 squared, 3/4 times 2. So what is that? Negative 3 halves. So that's why the answer is negative 3 halves. But if you take a look at the picture and we go back to negative 1 half, look at that. There's the height that shows that both sides of the graph are approaching that same height. Okay, so graphically we get the support on that function. Now, here's a limit, and this is the weird one. This one is going to be so steep because I've never seen a function with a power greater than 1,998. It looks like vertical lines because it's growing so fast. Luckily, they take the limit at a place that is easy to take the limit at, which is negative 4 plus 3 gives me a negative 1 in here. If it wasn't a 1 or a 0, we'd be in trouble. But negative 1 is either going to be, to any power, is either going to be negative 1 or positive 1. 1,998 is an even power, so the answer is positive 1. Okay, and it shows that that's exactly what we have here. But this graph was harder to graph because of its unbelievable power. I mean, that's a crazy exponent there. Number 9 is just a cubic. This one is a positive cubic with down-up end behavior and has a nice little couple turns in it. But if I plug a 1 in there, I'm just going to get 1 plus 3. So now I'm up to 4 minus 2. So now I'm down to 2 minus 17. So it should be negative 15 algebraically. This is work that you would want to show. So I think it's worked out in your course pack, but you definitely want to show that. But the graph should support that. And if we go over to 1, I do get a value of negative 15 on the graph. So you can see the graphs are supporting these substitutions. Remember, this is a problem at negative 2. At negative 2, there's going to be a hole right about here. So if I took the limit there, it would still exist because it's removable, but it would be not continuous there for sure. But we're not taking the limit there. We're taking the limit at positive 2. And so as you can see, it looks like we just have a continuous function that comes into about a value of 5. The algebra confirms that. I would get 5 squared root of 25 plus 25 plus 6 is 56 over 7. 56 divided by 7 is 56 divided by 7 is 8. Okay, so 8. 1, 2, 3, 4, 5. I wonder why my graph has 5. Oh, yeah, I must have done the math wrong. Let me see here. Oh, this is 5 times, not 5 times 5, 5 times 2. So 25 plus 10. Oh, 4 squared. So I was plugging a 5 in. I keep wanting to plug the answer in. So 4 plus 10 plus 6 is 20. 20 over 4 is 5. Yeah, absolutely. So the graph makes sense. I had to quit confusing myself. All right. Here's another 4 quick ones. This one has a couple vertical asymptotes at 3 and negative 3. And so, you got to be careful with that, except, okay, it looks like at the top numerator also has a y plus 3. So it looks like we actually have a hole. Instead. And if we look at the graph, it tells us that we're just coming in to 0 right here. And if you plug the 0 in, you would actually, or a negative 3 in, you would actually get 9 plus a negative 12 plus 3, so that's a 0. And then you get 0 on the bottom, so that would, no, you would, that's 9 minus 3. It's root 3 that you can't plug in. So that would actually be 6. So 0 over 6 is 0. Perfect. Yeah. It's at root 3 and negative root 3 where the asymptotes are, not at 3 and 3. So this is this isn't a perfect square 3. So here's the work actually as you see 0 over 6. Number 12 is our step function, and if we took the limit at any integer, the limit would not exist. Like if I took the limit as we approached 2, the left limit would have a height of 1, the right limit would have a height of 2. Oops. The limits don't agree, the overall limit doesn't exist. But luckily, that's not what we were doing. We're taking the limit as we approach 1/2, which just means we're on this constant step at a height of 0. So the limits from the left and right are both 0, and that means that the overall limit of that function as we approach 1/2 is 0. And the greatest integer of 1/2, the greatest integer less than or equal to 1/2 is 0. This guy right here, if I plug a -2 in, I get -8. The cube root of -8 is -2. -2 squared is +4. So I should get +4. Here's the work that we see, and here is the graph that confirms it. As I approach -2, I am getting a height of 4. All right, number 14 is the square root one, where if we were over here, we'd be in trouble. But because I'm over here, I'm fine. 2 plus 3 is 5. I'm approaching a height of square root of 5, which is about 2.2. And you can see that's exactly where I am, about 2.2 on the graph. All right, last two. So this is the one that might have freaked you out a little bit, but anything, even e to the 0, is just 1. And if you had forgotten your unit circle table, cosine of 0 is also 1. And so I just get 1 times 1 is 1, and then if you graph it, sure enough, as I approach 0 from both directions, right, as I come along here and then head up, as I come up this way from the right limit, my height is 1. And then the last one is the natural log of the sine. So this is a really interesting function. As I approach pi over 2, half of 3.14 is about 1.57, so a little more than 1.5 here. It looks like the height is 0. It looks like it. Now, what would confirm that algebraically is remembering that the sine of pi over 2 is 1, so that's a table value there. And then the log of any base, including the natural log of 1, is 0. Remember, that's because anything that's raised to the 0 power is equal to 1, right? We remember that. So that's where that rule comes from. All right, last for our thinking problems, and this really leads into Wednesday's lecture, okay? Because Wednesday, we're going to start hitting problems where you no longer can use substitution. That's where things become much more interesting and mathematically complex. I cannot put a -2 in here because I would get a negative radicand under a square root. Well, that's an imaginary number. I cannot put a 0 in the denominator of a fraction, whether it's here or here or here. And so if you can't put the value into the function, you cannot use substitution. And that's where we're heading tomorrow. Now this asks to explain why you can't use it. And we kind of just did. Here we would get an imaginary number. -2 is not part of the function's domain. Here I would get a 0 in the denominator. Here I would get a 0 in both the numerator and the denominator. Here I would also get a 0 in both the numerator and the denominator. Remember, zeros in just the denominator is usually a vertical asymptote. Zeros in both the numerator is going to be a hole. So probably we'll get holes here. Why does that matter as far as limits go? Infinite discontinuities don't have limits, but holes are removable discontinuities. The limits will still exist, okay? And they want us to find if the limits exist by graphing them, and so we can do that. So let's take a quick look at these four. Here's number 17, and we already talked about why we can't evaluate it. -2 is is not part of the domain. It's not defined there. Because the square root of -5 is not a real number, the limit does not exist. But we know what square roots look like. We know that this is the square root of x, and so the -2 shifts it over, okay? And because we're trying to evaluate the limit back here, it just can't happen. It can't be done. And you can graph it on your graphing calculator and get the exact same thing. It's impossible. This guy right here has an x squared in the denominator, which we can't have zeros in the denominator. Okay, you cannot have zeros in the denominator. Now, we know that 1 over x would look like kind of like this, and kind of like this. What the 1 over x squared is going to do is it's going to make these go up and down faster, but it's also going to make all of the values positive, right? Because when you square negatives, you get positives. So you're going to get two branches that are both going up, and it's going to look more like this. Oops. Except maybe down here. Um, in the graph on your calculator will give you the same thing. But look what happens at 0. At 0, we're undefined, right? Because we're approaching infinity. Now, that's a problem as far as limits existing, because infinity is not a real number. And so on this one, you pretty much just have to say the limit does not exist. 19 is a different story. It has a 0 in both the numerator and the denominator. And so in some cases, you're like, well, maybe that's just a hole and the limit exists, right? You still can evaluate the limit by substitution because you can't have zeros in the denominator. It's undefined. But if you think about what the values would be here, you can really understand whether a limit will exist or not. If I put any positive number into this, I'm just going to get a number divided by itself. Anything divided by itself is 1, right? On the other hand, if I put any negative number into this, I'm going to get a positive number because the absolute value will make it positive divided by its negative self. Oops, that's a -1. So there is a jump discontinuity, which means the limit would not exist, right? The left limit is -1. The right limit is +1. And so that's a problem. But why can't we evaluate the limit by substitution? Because you can't have zeros in the denominator. Here's the graph of the function on the calculator. You can see it's the same thing we just got there, doing it by hand. Finally, we end up with number 20, which looks like just a standard problem that's undefined, except when you look at the graph, I don't see any vertical asymptotes. There's no vertical asymptote at 0. That's because through cancellation, you will be able to get rid of that x in the bottom, and that's the type of problem we're going to look at tomorrow. But in the meantime, I would say you can't evaluate the limit through substitution because we're not allowed to divide by 0, just like we have been saying on a lot of the other problems. Furthermore, I would say that the limit does exist. It turns out that you have a hole at 0.8, and you could get that through your graphing calculator. Look at that. At 0, it's undefined, but look what height it's approaching on your tables. If you go to your table of values, okay, or even just look at, 1, 2, 3, 4, 5, 6, 7, it looks like we're getting really close to 8 from both sides here. So that's the limit. And I think that pretty much finishes off this assignment. Hopefully, if you were getting stuck anywhere, this helped kind of get you a little more understanding. And tomorrow we're going to have a lot more algebraic intensity as we go through these types of problems right here and how can we fix them. Sometimes we can't, like 17, 18, and 19, there's really nothing we can do, but 20, there's a way around it, and it's really just algebraic. Hopefully, yeah, have a good day on Wednesday, and we'll talk to you on the next lecture.